Welcome to our short discussion of heat and mechanical equivalent of heat. Heat and temperature and thermal energy often get confused with each other. Heat is really just the transit of energy. It is the energy moving from one substance to another. Thermal energy is really the energy associated with all the energy, kinetic energy, and other types of energy that are associated with the system or the substance itself. And temperature is really related to the average kinetic energy of the molecules. Okay, so it's really how hot or cold a substance is microscopically. Microscopically, temperature is really just related to the kinetic energy per molecule. Okay, let's talk about when you know that heat occurs. So let's say you have two systems. You have T1 here and T2, and we'll say this is hot here and this is cold. So if you have two systems that come in contact, and this is a conductor in here so that heat can flow, we'll see that heat will always flow from hot to cold spontaneously. So the energy will flow in this direction from T2 to T1 if T2 is greater than T1. So as the energy flows, that thermal energy flows from here to here, the temperature T2 system will drop, and consequently the temperature T1 will go up until they eventually reach the same temperature T1 and T2, and then at that point we say that they are in thermal equilibrium. So thermal equilibrium occurs when the two objects have the same temperature. Now, to start off, both temperature 1 and temperature 2 were identical, or both say 100 Celsius, then the heat flow would be 0. Because in order heat to flow from one system to another system, there must be a difference in their temperatures. There must be a difference in their average kinetic energies. So, hopefully you understand that heat is really not a form of energy, but is a flow or transit of energy from one system to another system. Now, heat was really confused historically. Now, originally, the units of heat were defined in terms of water. You can see down below here, you'll see that the units of heat were initially written as a calorie. And a calorie was the amount of heat or heat energy that was needed to raise the temperature of 1 gram of water up 1 degree Celsius. Later on, it was realized historically by James Joule that 1 calorie was equivalent to 4.186 joules. And he did that in this very famous experiment, which we now understand this as the mechanical equivalent of heat. He showed that when heat transfers from one place to another, work must have been done. Sir James Joule discovered this by creating a contraption where he had a water in this cylinder here, which was heated as these paddle wheels started to churn the water. And so what he found out was that this rise in temperature, he has a temperature thermometer here, and he found that that change in temperature was in direct proportion to the work that was done by this mass. So you see this mass, as it falls, it loses potential energy, which then causes this to spin, causing these wheels to turn around, and he started to notice that as he did work over here, the temperature of this substance started to increase. And so gradually people started to realize that really heat is just a form of energy. It's the transfer. It's not a form of energy, sorry, it's the transfer of some energy. So it was this experiment and many others that were similar to this that showed that heat flow is the energy transfer that is equivalent to between heat and work. So let's take a look at example number 1. Really, all you have to realize is that if I ask you to find the heat transfer in the liquid here, Q, all you really need to do is find the external work that was done. So the concept of mechanical equivalent of heat basically says that Q is equal to W. The heat that was transferred from one system to another is equivalent to the work that was done. Now the work that is done in this picture, you can see you have a mass M given, you have a distance H given, and you know that it's done 20 times. So hopefully you realize that the work done is the change in potential energy, and this is being done 20 times. So that's mgh multiplied by 20. Or you could say the mass is 12 kilograms times 9.8 meters per second squared times a height of 1.25 meters, and this is being multiplied by 20 because you did the process 20 times. So therefore, you get an answer of 2,940 joules of work done, which is the same amount of heat that flowed. So this is equivalent to 2.94 kilojoules. By the way, if I have not mentioned already, heat is also written in units of calories, so you could, if you'd like to report this in calories, we would just simply multiply by 1 calorie over 4.186 joules. This would give you an answer of 702 calories. There are other units of kilocalories, which is 1,000 calories, but in depending where you are, in Singapore, you'll see they'll use kilocalories often in food. In some places in North America, they actually don't call it kilocalories. They'll write a capital C calorie, which actually represents like 1,000 calories. BTUs is another unit that's used still commonly. It's an old British thermal unit. It's used in furnaces and barbecues, and it's really based on the fact of how much energy that would be flowing from one place to another to raise the temperature of 1 pound of water up 1 degree Fahrenheit. And this is what 1 BTU is equal to in calories and joules. So remember that heat is just really energy in transit. Alright, and that's it for this example and our discussion of heat.